Welcome back to Linear Algebra. I'm Dr. Jeff Groh. Today we're going to talk about linear independence. I'd like you to remember that by definition, we say that vectors u and v are parallel if either first u is a scalar multiple of v or v is a scalar multiple of u. We are being a little cagey here. We're not excluding the possibility that one of these vectors is the zero vector. For instance, if u is the zero vector, then we could rescale v by the scalar 0 to give you the zero vector u, but it wouldn't work the other way around. If v was not the zero vector and u was, there's nothing you can multiply the zero vector by to get something that's not the zero vector. So we have to have both of these conditions. We write u is parallel to the vector v. In 3-space, let's suppose you have a couple vectors, u and another vector that is not parallel, v. Those vectors lie in a common plane. What is more, if you have some point in the plane, you can go a certain number of units along one vector direction, a certain number of units in the direction of the other vector, to get to that point, as long as, of course, the plane is going through the origin. In other words, every vector in this plane going through the origins, w, the vector w, can be expressed as a multiple of u plus a multiple of v, a linear combination. Let's suppose u is the vector 2, 1, and v is the vector 4, 2. Clearly, v is twice u. This means that negative 2u plus 1v is equal to the zero vector. We have a linear combination of these parallel vectors that adds up to the unit vector. If u and v were not parallel, would it be possible to have a non-trivial linear combination that gives you the zero vector? Consider the following example. Let's look at E1, which is 1, 0, and let's also look at E2, which is 0, 1. Arbitrary linear combinations, C1, E1 plus C2, E2, add up to C1, C2. If that equals the zero vector, that's true if and only if C1 and C2 are 0, the trivial linear combination. E1 and E2 are your prototypes for vectors pointing in non-parallel directions in the xy plane. A set S of vectors is called linearly independent if for each finite subset x1, x2 through xn of S, the only linear combination equal to the zero vector C1, x1 plus C2x2 plus Cnxn equals 0, the only linear combination that gives you the zero vector is the one where all of the coefficients are 0. This, by the way, is the trivial solution to this equation. It's obvious that if you select all of the coefficients to be 0, you will get the zero vector. At issue is whether or not there exists non-zero coefficients where the vectors add up to the zero vector. As we've seen, if vectors are parallel, there will be a non-trivial linear combination where they add up to the zero vector. If they're not parallel, it looks like they won't. Also, but when you have a collection S with quite a few vectors, the question becomes how many different independent directions can you have? If some of those vectors aren't pointing in different independent directions of the others, the set is not going to be linearly independent. On the other hand, the set S is linearly dependent if it is not linearly independent. Okay, I know that's a half-assed definition. It works, but what does it really mean? I.e., for id est, there is a non-trivial linear combination where C1x1 through Cnxn equals the zero vector for some finite subset within the set S. In particular, not all of the C's are 0, and that's what it means to be non-trivial. Parallel vectors are linearly dependent. You can always express one as a multiple of the other, and so in some sense, you don't really need the one. All of its information is encoded in the other one by scalar multiples. Similarly, if you have three vectors, that have a non-trivial linear combination equaling the zero vector, let's suppose without loss of generality, that C1 is not 0. That implies that V1 can be expressed as minus C2 over C1 V2 minus C3 over C1 V3. In other words, we can construct V1 by a linear combination of the other two vectors. So all the information encoded in V1 is already encoded in these other two vectors. We don't really need this one. The set is linearly dependent. In B. In B is the abbreviation for the phrase nota bene, note well in Latin. The standard ordered basis for Rn is linearly independent. Each of the vectors in Rn encodes new information. It gives a new independent direction. And we can see that because if we take C1E1 through Cnen, that gives us C1 times 1 zeros, Cn times 0 down to 1. What you end up with is C1, C2 down to Cn. If that's equal to the zero vector, which is all zeros, that's true if and only if all of the C's are 0. That's exactly what it means to be linearly independent. The only linear combination that gives you the zero vector is the trivial one, where all of the coefficients are zero. Let me write, therefore, the collection E1 through En is linearly independent. I really need you to understand these concepts of linear independence and linear dependence very well. Let's look at another example. Suppose I have V1 equal to 1, 0, 0, 0. This is in your four-dimensional Euclidean space, R4. V2, let's say 1, 0, 0. And V3 equals 1, 0, negative 1, 0. Are these vectors linearly independent or linearly dependent? We can find out. We'll take C1 times V1 plus C2 times V2 plus C3 times V3. And what do we get? We get C1 plus C2 plus C3 for the first coordinate, and then C2 for the second coordinate. The third coordinate will be minus C3, and the fourth coordinate will be 0. If this adds up to 0, 0, 0, 0, that can only happen if C2 is 0, C3 is 0, and if both C2 and C3 are 0 and C1 plus C2 plus C3 0, that implies C1 is also 0, which means all of the coefficients are 0, and therefore these are linearly independent. As another example, suppose I give you V1 equals 1, 1, V2 equals 1, negative 1, and V3 is 3, 4. Are these vectors linearly independent or linearly dependent? Let's find out. We'll have C1 times 1, 1 plus C2 times 1 minus 1 plus C3 times 3, 4 equal to 0, 0. Is there or is there not a non-trivial linear combination that gives me the zero vector? We have to solve the system. C1 plus C2 plus 3C3 equals 0, and C1 minus C2 plus 4C3 equals 0. Isn't it interesting how all of these issues resolve into a system of equations? Let's solve this using an augmented array. We'll have 1, 1, 3, 0. 1 minus 1, 4, 0. We'll take negative row 1 and add to row 2, yielding a new row 2. That leaves the first row alone. Negative 1 times this plus this, negative 1 times this plus this, negative 1 times this plus this, and negative 1 times this plus this. You can see then, it looks like we will get some non-trivial solutions. The last equation represents minus 2C2 plus C3 equals 0, or C3 is twice C2. If we set C3 equal to 2, then C2 equals 1. The first row represents the equation C1 plus C2 plus 3C3 is 0, but we've already chosen C2 to be 1 and C3 to be 2. That means C1 is minus 7. This gives us a non-trivial linear combination for the vectors to add up to 0. Since a non-trivial solution exists, we deduce that these vectors are linearly dependent. You can see then that we have negative 7 times 1, 1, plus 1 times 1 minus 1, plus 2 times 3, 4, equaling 0, 0. Negative 7 and 1 is negative 6, and 6 makes 0. Negative 7 minus 1 is negative 8, plus 8 makes 0. It follows then that we can solve for one of these vectors in terms of the other. Let's suppose we're looking for 1, negative 1. That's going to be 0, 0, minus a negative 7 times 1, 1, and then minus twice 3, 4. In other words, we can express the vector 1, negative 1 as a linear combination of the other two. What do we need this one for when we can construct it from the other two vectors? You can see from the last example where we constructed the augmented array, from the very outset, that the reduced echelon form would be of the form 0, 1, a 0 below, a 1, and then we would have a free variable. There had to exist a free variable in this case because we had too many columns. That corresponds to too many vectors to begin with. We had 3 vectors in a 2-dimensional space. And so because we had this free variable, there was going to be a choice that we could make for that C3. Once we had that, everything else would fall into line. We'd have a non-trivial linear combination expressing one vector in terms of the others. We can generalize this in the following theorem. If S consists of the vectors v1 to vn, where S is a subset of Rm, and n is strictly bigger than m. So the number of vectors that you have is larger than the dimension of the vector space that you are in. Then S is linearly dependent. It has to be. You have too many vectors in too small a vector space to have linear independence. This theorem is important. It tells us if you have a particular size vector space, if you get too many vectors, you can tell just by the number of vectors that that set is linearly dependent. The proof goes as follows. The equation C1v1 through Cnvn equals 0 produces the augmented array A0, where A is the matrix V1, V2 through Vn. Now, because each of these vectors is in Rm, you have m rows, but you clearly have n columns. That means this will have m rows and n plus 1 columns. This, because you have so many more columns than you have rows, is underdetermined. Because this system of equations is underdetermined, and it does have a solution, namely the trivial solution, you can tell that it has infinitely many solutions. Remember, for systems of equations that are homogeneous, there are only 2 cases, a unique solution or infinitely many. And every time you're dealing with an underdetermined homogeneous system, you have to have infinitely many solutions. That means there do exist non-trivial solutions. We deduce then that the vectors are linearly dependent. In our next example, what if your collection of vectors already has the zero vector in it? Isn't it linearly dependent? The answer is sure. I'll just take any number at all, like 5 times 0, 0, plus 0 times 1, 0, and that gives me the zero vector. Just take any scalar multiple of the zero vector and zero everything else out. You'll get a non-trivial linear combination that adds up to the zero vector. We'll have the following theorem. If the zero vector is an element of a set, then that set is linearly dependent. The proof goes just like before. Let this be a subset of S. We can take 1 times 0 plus 0 times V1, 0 times Vn, and that does in fact give you the zero vector. Because this is a non-trivial linear combination yielding the zero vector, we deduce that S is linearly dependent. We also have the theorem that we've kind of been referring to or talking about. The set S is linearly dependent if and only if at least one vector in S may be expressed as a linear combination of the others. So that vector does not give new information that can't already be constructed from the others. We'll prove this. S is linearly dependent if and only if there's a linear combination that's non-trivial not all of the C1s through Cn's are zero. Without loss of generality, W log, without loss of generality, suppose C1 is not zero. Then this equation holds if and only if. You have to think about what you get when you move all the terms except for V1 over. We're going to solve for V1. You get minus C2 over C1 V2, and then minus Cn over C1 Vn. In other words, V1 can be expressed as a linear combination of the others. V1 is a linear combination of the others. For example, suppose our set S contains 1, 0, 0, 1, 1, 0, and then 3, 2, 0. Check it out. 3, 2, 0 is 1 times 1, 0, 0 plus 2 times 1, 1, 0. That means the last vector can be expressed as a linear combination of the first two. Therefore, S is linearly dependent. We have the following theorem. If S is linearly independent then any subset of S is linearly independent. You can't get dependence by taking vectors away, only by throwing them in. If S linearly dependent and S is a subset of some larger set U, then U is also linearly dependent. If you can already express some vector as a combination of the others, throwing more vectors in doesn't cure the situation. You can still represent other vectors by vectors within the set. In analyzing the proof, I want to think about the logical structure. Let U be a subset of S. This is for part 1. We're saying that if S is linearly independent, then U is linearly independent. What is the contrapositive of this statement? Remember, if you have a logical implication A implies B, the contrapositive is not B implies not A. And a logical implication and its contrapositive are logically equivalent. Remember the phrase, if I am in Paris, then I am in France. Let's suppose that that is a true theorem. The contrapositive is, if I am not in France, then I am not in Paris. That too is true. In fact, it's possible to show, and it is shown in a course in mathematical logic, that a implication like this and its contrapositive are always logically equivalent. So if we can prove contrapositive, we will have proved this statement. The contrapositive is, if U is linearly dependent, then S is linearly dependent. Let's prove the contrapositive and then deduce that the original statement was true. Suppose U is a subset of S and U is linearly dependent. What does that mean? That means we can find a finite set of vectors in U that has a non-trivial linear combination equal to the zero vector. But U is a subset of S, which means this collection of vectors is also a subset of S. We have a non-trivial linear combination of vectors in S equal to the zero vector, and that means S is linearly dependent as well. Since U is a subset of S, we see that V1 through Vn is also a subset of S, and we have the same non-zero coefficients giving us a linear combination equal to the zero vector, and that implies S is linearly dependent. This, by the way, also proves the second part of the theorem, the same argument. There's an important theorem we need to write down. If S linearly independent and V may be expressed as a linear combination of vectors in S, then there are unique constants and vectors C1 through Cn, V1 through Vn contained in S, such that V is C1 V1 to Cn Vn. We've already assumed that V may be expressed as a linear combination of vectors in S, so it's not surprising that we can express V in this form. What's surprising is that there's only one way to do it, one choice of the vectors and one choice of the constants. The proof is in some ways a typical uniqueness proof. To prove there's only one of something, you suppose there are two, and then prove, in fact, they have to be the same. We're going to suppose that the vector V can be expressed as a linear combination of vectors in S in two different ways. Suppose V looks like C1 V1 out to Cm Vm, and V can also be expressed as D1 W1 to Dn Wn. And let's also suppose, without loss of generality, that n is greater than or equal to m. Now, we haven't precluded the possibility that some of the vectors in the set v1 through vm aren't also in the vector set w1 through wn. We're going to suppose v1 equals w1, v2 equals w2, up to some level vk equals wk. And VL won't equal WS for L greater than K, S also greater than K. So none of the V's at the end will equal the W's, and none of the W's at the end will equal the V's. It's at this point we'll subtract these two representations. Now, most of these now will have C1 minus D1 V1 plus C2 minus D2 V2, and this will proceed out until we get to CK minus DK VK, and then we add on the linear combinations of those terms that are left over. We'll have CK plus 1 V1, K plus 1, through CM VM, and then minus D K plus 1 W, K plus 1 minus D N W N. But wait a minute, we said the set S was linearly independent. So any linear combination of elements of S that equals the zero vector must have all coefficients equal to 0, as long as those vectors are distinct. None of these Vk plus 1 through Vm are represented in these Wk plus 1 through Wn's or vice versa. Therefore, all of the coefficients in this sum must be 0. Since S is linearly independent, we get ck plus 1 through cm equals 0, and all of the d's at the end are 0. dk plus 1 through dn is 0, and these other coefficients must also be 0. C1 will have to equal D1. C2 will have to equal D2, down to CK equals DK. So we see that any linear combination that two different sets that give us a linear combination that adds up to the vector v must in fact have exactly the same number of elements with the same number of non-zero coefficients. And those coefficients for the common vectors will be the same. This will end the proof. I want you to recall that the system A equals B is consistent if and only if B is a linear combination of the columns of A. Remember, if A can be written as A1, A2 through AN, then AX will be X1, A1 to Xn, AN, a linear combination. If that's all equal to B, then B is a linear combination of the columns of A. If B cannot be expressed as a linear combination of the columns of A, then the system is not consistent and hence has no solution at all. We can now state the following theorem. Suppose AX equals B is consistent. Then it has a unique solution if and only if the columns of A are linearly independent. Note that this is an if and only if statement, which means we need to prove the implication in both directions. We need to prove that if the system has a unique solution, then the columns are linearly independent. And we need to prove that if the columns of A are linearly independent, then the system has a unique solution. We have to do it both ways. Remember, the theorem basically states unique solution, and an exclamation mark is the mathematical symbol for uniqueness. If and only if columns of A linearly independent. So in our proof, we'll begin with the implication in this way, and we'll prove this by way of contrapositive. The contrapositive is columns of A linearly dependent, the opposite of linear independence, implies no unique solution. So we're going to suppose the columns of A are linearly dependent. What does that mean? That means there's a non-trivial linear combination that gives you the zero vector. There exist constants. We'll call them C1 through Cn, such that not all of these are zero, and we get the zero vector being a linear combination of the columns of A. Since A equals B is consistent, there exists a solution. We'll call it x hat. So A times x hat is in fact equal to this B. We're going to set y equal to x hat plus the vector C1 through Cn, where C1 through Cn are these constants. Then y is not equal to x hat because that's not the zero vector at the end there. C1 through Cn are not all zero. And ay is a times x hat plus this vector C1 through Cn. We can distribute to obtain ax hat plus a times C1 through Cn. Now we know what ax hat is. Ax hat is b. But what is a times this vector involving the c's? That's C1a1 through Cnan, a linear combination of the columns of A, and those add up to 0. So the whole thing is equal to B, which means we not only have a solution x hat, we have another solution y. Ay equals B, and y is not equal to x hat. That means that the system does not have a unique solution. So our assumption that the columns of A were linearly dependent implied that the system does not have a unique solution. By contrapositive, if the system has a unique solution, then the columns of A must be linearly independent. We have only to prove the implication in the other direction, that if the columns of A are linearly independent, then the equations have a unique solution. We'll prove this also by way of contrapositive. We'll suppose Ax equals B does not have a unique solution. We know it has a solution because we've assumed that the system is consistent. So we'll let x1 and x2 solve Ax equals B. Then we'll consider A times x1 minus x2. By the distributive law, we can write that as ax1 minus ax2, and that's b minus b, which is 0. That means that if y bar is x1 minus x2, then y bar is not the zero vector because these are not the same, and a times y bar is the zero vector. If y bar has coordinates y1 through yn, then we get the zero vector is y1 times a1 plus y2 times a2 plus yn times an, and that gives us a non-trivial linear combination of the columns of the matrix A that adds up to the zero vector. That implies that the columns of A are linearly dependent, and that is the end of the proof. This analysis is giving us a much better understanding of the solutions to systems of equations. I want you to recall, if A is square, then ax equals b has a unique solution if and only if A inverse exists, and that's true if and only if the determinant of A is not 0. We can add to this list now. We now know that ax equal b will have a unique solution if and only if the columns of A are linearly independent. So we'll add that to this list. We have the following theorem. Let A be an n by n matrix. The following are equivalent. A is invertible. Ax equals b has a unique solution. Ax equals 0 has only the trivial solution. A is row equivalent to the identity matrix. The determinant of A is not 0, and now finally, the columns of A are linearly independent. We have 6 items that are logically equivalent, and we are not done adding to this list.